Everyone, welcome back. So let's try another problem. So in this one I have an orthorhombic unit cell, for which A, B, and C last parameters are these values. And it wants me to figure out what is, let's see, the atomic radius, as well as the atomic weight. And it gives me some information. If you don't remember what orthorhombic is, it just simply says I don't have a perfect cube, like I have in the past, where A is the length of each side. Instead, each side has its own specific length. So this is B, this one right here could be A, and this one right here could be C. But otherwise, it's still like a nice boxy shape. It's still got 90-degree angles. So using that information, let's go ahead and solve this. So it says if there are 8 atoms per unit cell and the atomic packing factor is 0.571, determine the atomic radius. Well, this isn't too bad. So atomic packing factor, don't overcomplicate what it is. All it is it's saying, okay, what is the volume of the atoms inside of the cell over the volume of the cell itself? Now, since this is orthorhombic and it's just a nice little box shape, the volume of the cell is really easy. The volume of the cell is simply equal to A times B times C. And if I plugged it in, I would get a value of 0.270 nanometers cubed. So that's the bottom. Now, what is the volume of the atoms? Well, it tells me that there are 8 atoms per unit cell. And all my atoms, we're going to just assume that they're nice, perfect spheres. So my volume of atoms will be equal to 8 times 4/3 pi r cubed. 4/3 pi r cubed is the diameter, or sorry, it's the volume of a sphere. So if I use this, I can then rearrange to solve. So what I'll get then is 0.571 is equal to 8 times 4/3 pi r cubed all over the volume, which I already calculated, which is 0.270 nanometers cubed. And if I rearrange to solve for r, I'm not going to bother doing the algebra, you can do that on your own time. It will come out to be a radius of, let's see here, 0.166 nanometers. Beautiful. Now the second part of this problem says, if the density is 5.87 grams per centimeter cubed, calculate the metal's atomic weight. Okay. So we're trying to find the atomic weight A, and that's always the whole, like, what is the grams per mole? It gives you density, so let's build it out from density. So density is equal to mass over volume. I already have the volume, that's the volume of the cell. But what about mass? How do I get mass? Well, look at atomic weight. Atomic weight is grams per mole. And so if I was trying to get mass for that, I would have to take into account how many I have. So in this case, my mass is going to be equal to my atomic weight times Avogadro's number. But here is the issue, and here's the thing you have to be very careful of with as you're doing this. Let's see. Oh. One, make sure you don't make mistakes like I do. So let's check it out with units so we don't make the mistake I was just about to make. So mass should be grams. I have the atomic weight, which is grams per mole. So I have Avogadro's number, which is atoms per mole. And then I want to have just grams. So to get my mass, I would have to divide by atoms per mole. There we go. And then finally, I would have to cancel out atoms, and so I'd have to multiply by the number of atoms. Okay, so looking at just the units here, building it up, I get that mass is equal to my atomic weight times the number of atoms divided by Avogadro's number. That should work. The units cancel out, and it looks good. So let's plug that back into my initial equation and I can rearrange. So density is equal to my atomic weight times the number of atoms all over the volume times Avogadro's number. That looks perfect. And if I rearrange so I have my atomic weight, I would get that is equal to the density times Avogadro's number times the volume all over the number of atoms I have in my unit cell. Now, these are all values that I currently have, though I have to be very careful because my volume is currently in nanometers cubed. I would have to convert that to centimeters cubed at the very least. And so let's just plug in these numbers and I'll show you how I convert. And where is it? Ah, there's my, up here a little further. 5.87, that's the density, okay. 5.87. So 5.87 grams per centimeter cubed times Avogadro's number, 6.022 times 10 to 23rd, times the volume, which was, let me see, 0.27, okay. 0.270 nanometers cubed, all over 8 atoms. Fantastic. So, how do I go from nanometers to centimeters? Well, we'll just do it to meters, and that'll work out a little bit easier on us. So how many centimeters are in a meter? Well, there's 100. And how many nanometers are in a meter? There is 1 billion. So that's the conversion I would have to do 3 times. So with that, I have everything. And so what I'm going to do now is I'm going to plug that into my handy dandy calculator. And I get 0.458 grams per mole. Yeah, works out nicely. If you're wondering how I plugged that in so quickly, I had that one already pre-calculated. Not all these were pre-calculated, but that one was. So hopefully this helps you. Thanks for listening. I'll see you all next time. Bye-bye.